Bienvenidos, Ushamdid, and welcome University of Maryland Global Campus learners from the CMIT-456 Section 6380 course for the fall 2021 semester. This is the Cisco Networking Academy's CCNP ENARSI version 8 course curriculum, and in this packet tracer tutorial and activity, we're going to be taking a look at packet tracer 7.2.1. where we're going to talk about and configure some advanced OSPF features. Now, first thing to note as we jump into Packet Tracer here is that there is a new version of Packet Tracer that was recently released, and that is Packet Tracer version 8.0.1. Now you can see here we've got the .0064, but again, 8.0.1 is out. It's got some nice enhancements to it in terms of user experience, so I would highly recommend downloading that, and these ENARSI activities are going to work with 8.0.1. All right, so into the activity we go. Here is our addressing table over here to the right, and our objectives are going to be to modify some OSPF default settings. Now, I'm also going to be providing some value add here when we talk about the why and when you would actually make these types of changes. So, right out of the gate, they want us to test connectivity between all the devices before modifying the OSPF settings. And so, in other words, if I was to pull up PC1 here, and we'll drop this down over here to the side, I should be able to, from the command prompt, which, now that we have a new version of Packet Tracer, and so this may come up for you as well. So if you wanted to enlarge the font size, you would go into Preferences, you're going to come into Font, and you can see here the dialogues for the CLI. It's at 10. Well, we want that to be the max of 20. Tooltips, same thing. Let's max those out. Let's click Apply, and we're going to go ahead and shut that down. So now I'm going to click on PC1. We're going to bring PC1 back down here, and let's go ahead and go to the command prompt, and now we can see what we're doing. So from PC1, if I was to try to ping PC2 at 172.16.2.2, let's see if we've got connectivity. And while that is thinking, we're going to pull PC2 up. We'll be running some tests here from PC2 and give ourselves some room with which to work, as well as PC3. Now, we're probably going to drop that first packet on PC1 as we ARP out for our default gateway, which is going to be what I believe is the gig 00 interface there on router number 1. As you can see, that is what that means, that request timeout. It means that we did the ping command on PC1, and PC1 did not have in its routing table anything configured to get to that network, right? There was no specific match for that network, and so we have to ARP out for the default gateway because we don't know, PC1 doesn't know how to get to the default gateway. So now that we've got that sorted out, we get our ping replies back. So let's go ahead, and if we can get to PC2, can we go from PC2 to PC3? And again, we're just making sure that 192.168.1.2, we're simply making sure that we've got connectivity throughout the environment. And why not kick off the same command over here, trying to get to 192.168.1.2. And so PC1 can successfully get to PC3, PC2 can successfully get to PC3, meaning PC3 can get to both PC1 and PC2. All right, so we're good to go. Now here is what they want us to modify on router 1. And specifically, they want us to do this to the serial 000 interface. Now that interface is the interface that runs between, and if we were to come up here, you can see 000. It's a 172.16.3.1. It runs between router 1 and router 2. In other words, it's this transit segment here between router 1 and router 2. And what they're going to want us to change is the hello and the dead interval. Now, let's see, with previous versions of Packet Tracer, what happens in the real world with real Cisco IOS and what happens with Packet Tracer can sometimes be confusing because sometimes it's different behavior. So we're going to find out what that behavior looks like here with the new version of Packet Tracer 8.0.1. Now, if I was to say show IP OSPF interface, and let's see if they've got the brief command in here. Okay, so 8.0.1 doesn't have show IP OSPF interface brief yet. That would be a great add-on here. That command exists in the real world on real Cisco IOS. But let's go ahead and we'll just simply say show IP OSPF interface. Now the serial 000 interface is the interface that we are interested in here, and let's pull out the drawing tool for just a second and make sure that we've got red selected as the color. And this is the command that you can issue that will show you a lot of information about the interface in question. And specifically, we are looking at the timer intervals. Now, the default timer intervals for point-to-point and broadcast OSPF network types is that the hello is 10 and the dead is 40. Now, the wait timer, this is inextricably linked to the DR BDR election process. Now, we're not going to be covering that here, but know that that's what the wait timer is all about. So, hello packets on point-to-point network types in OSPF by default will be sent every 10 seconds. The dead interval is how long an OSPF router will wait before declaring the adjacency to be dead. And so in other words, it's 4 times the hello interval. Now, in real iOS, when you change the hello interval, the dead interval will auto-magically adjust to 4 times whatever you set the hello interval to be. So let me demonstrate that here by jumping out to 2 routers that we have set up here, router 8 and router 9. If you've seen any of my previous videos, these are the routers I have on 24/7 so that I can jump onto them if I need to. So we're going to get into global config, and I'm simply going to say router OSPF1. And let's go ahead and say router ID. This is router 8. It's just going to be 8.8.8, or actually we'll do a 0.0.0.8. We're not going to do any passive interface type work. And then let's go into interface serial 000. We're going to say IP OSPF1 area 0. And now let's come over here to router 9. And actually, before we do that, what if I was to say do show IP OSPF interface brief? That is what I was looking for, and that's kind of what I like to see when I'm looking at some of the interface information. This is a nice command to trim a lot of things down. Now, you could always say do show IP OSPF interface serial 000 if you only want to see a single interface. Without specifying the interface, you're going to get all interfaces. Now, you'll notice that the timer intervals here are identical to what we're seeing over here in our packet tracer activity. Hello 10, dead 40, wait 40, retransmit 5. Right? And as that's what we would expect to see. And that's what we see here. And again, this is a serial interface, and it's point to point, and it's back to back, because these routers that I have here at my house, they're connected literally from the serial port right into the serial port on the other router. There's nothing in between. And so here we have our defaults, 10 and 40. In other words, the dead interval is 4 times the hello interval. So 4 times 10 is going to give me 40 for the dead interval. That's how long I'm going to wait. In fact, if I was to pop out here and say debug IP OSPF, OSPF packet, and then we're going to want, let's see, I want to go debug IP OSPF. I think we want to say, yeah, we want hello is what we're specifically looking for. So we want hello to specifically see the hello packets. Now, what we should see is that every 10 seconds, and there we go, and you've got your timestamp right down here, every 10 seconds you can see OSPF process ID 1, I'm sending a hello, out serial 000, and I'm sending it out to this multicast, this all OSPF speakers, right? This is all OSPF routers. That is the multicast address for all OSPF routers. That is the address which other OSPF speakers are listening on or listening to. They're looking for this traffic that's headed multicasted to that address. And you can see that I'm in area 0, and that is the IP address of the interface, right? So let's come over here to router number 9, and let's go ahead and set up an adjacency here. And again, remember, this is a serial interface over here, and I'm going to show you router OSPF, and let's say 99, because I want to show you things that don't have to match. And the process ID number in a configuration context like this does not need to match. Now, when you get into MPLS Layer 3 VPN and some more advanced CCNP studies, and that may be on the CCIE edge there, you'll start to talk about this, where maybe this is a consideration where you're going to want to have the process IDs of OSPF match for specific reasons as to whether you're going to see a type 3 or a type 5 LSA with routing information coming across that backbone, or I should say the MPLS backbone. Okay, so router OSPF 99, let's go ahead and we'll throw a router ID on here of 0009. And then let's get into serial 000 IP OSPF 1 area 0. So now that we set this up, you'll notice how quickly, again, these are connected back to back, and there's nothing else going on these routers, that we went from loading to full. Now, again, there are, in the OSPF state machine, there are other states, down, two-way, etc., but then we end up here going from loading to full. So if I was to say do show IP OSPF interface serial 000, this is what we see. The hello and the dead intervals are set here. Now, what happens if I say IP OSPF? Now, remember, I'm under the interface. This is where this adjustment gets made. So I say IP OSPF 1, and if I do a question mark area, I'm sorry, I didn't want 1, IP OSPF, and when we look here, we can see that here is the dead interval. Here is the hello interval. And so what happens if I change the hello interval from the default of 10, and you can see these are the ranges of values that you have available, from 1 to 65,535. Now, 65,535 is probably something you're never, again, at the end of the day, the defaults are the defaults for a reason. And typically, you're not adjusting the defaults unless you have a very compelling reason to do so, or if TAC is asking, the Technical Assistance Center at Cisco is asking you to do it as some part of a troubleshooting activity, right? So IP OSPF hello interval, let me go ahead and set it to 15. Now, if what I told you is true, that the dead interval auto-magically adjusts, let's see if that happens here. Is that 4 times the hello interval? It is. Now, something else is also going to happen. Do show IP OSPF neighbor. So here's the dead time. It's at 13. It's at 9. Why is it not going back up? Well, it's not going back up to what we now have it configured for, which is 60, because the adjacency is now down. The hello intervals need to match, right? If the hello interval doesn't match, the adjacency is not going to come up. And if the adjacency is already up, as I just demonstrated here, and you change it on one side and not the other, the adjacency will go down in this point-to-point scenario. In a broadcast context, if you got 20 routers plugged into a switch and I change it on this one router, then this router is going to go, the adjacency between this router and all other routers is going to go down, right? So right now, do show IP OSPF neighbor, we don't see anything. And what did we see over here? It's probably pandemonium. Yes, as you can see. And what I like here is take a look right here. In the hello packet is where we see the dead timer values, right? And what we are receiving and what is configured. And this is our configured hello, right? I'm sorry. I'm sorry. Let me take a step back here. Let me stop this here. Let me say you all. And so we see here on the serial interface, right? We're receiving a dead timer value of 60. We have on our side, router 8, it's configured for 40. And in that same hello packet, we see that the hello interval, we're receiving 15 because that's what we changed it to on router 9, but we're configured for 10. Mismatch parameters, right? So debug IP OSPF hello, and that's going to show you if you've got these mismatch parameters. And it's actually going to show you what they're configured to be, what I'm configured to have here, and I want to say I, router 8, and what I'm receiving, that R. And that is going to take the adjacency down. So let's transition back out here to this activity. We've tested all of our connectivity, and now let's get into interface serial global config, interface serial 000, IP OSPF, hello interval 15. Now, there's a reason that I did what I did on real Cisco routers running real Cisco 15.x code. Watch what happens here. So actually, before I do this, let's go ahead and say, do show IP OSPF interface. Again, we come down to serial 000. You can see the defaults, right? So that's correct. IP OSPF hello interval 15, and then we rerun this do show IP OSPF interface. What did not happen? In Packet Tracer, and this is something that's been around for a very long time, it does not auto-magically increment the dead timer to the dead interval to 4 times the hello interval. And this can be misleading for learners who think that they have to change the dead interval value to get it to be 4 times the hello interval. You don't have to do that on real Cisco IOS. Do show IP OSPF neighbor. I want to squeeze this in real quick. And you can see 2 seconds, 1 second, and done, right? And we know why this is happening now. Mismatch timer values. Again, if the adjacency is up and you change the timer values and they don't match with OSPF, on this point-to-point scenario here, we've got ballpark 30 plus seconds to get the change done on the other side before the adjacency is going to go down. So you do have some time to make this happen. Now, if I'm doing this in a scenario where one router is in the building that I'm in and the other router is in Uzbekistan, I'm probably going to make the change on the Uzbekistan side first and then circle back or have both windows up to do it in that order to make sure that if I needed to, have the adjacency go down if it happens, that, hey, I can take care of it right here. I've got local access. So always do it on the remote side first before you do it on the local side. So after a short period, the OSPF adjacency went down. That happened. And again, we should still have connectivity between the PCs. And why? It's because OSPF is a dynamic routing protocol. And what that dynamic word means is it's going to reconverge and there will be a shortest path chosen for all traffic. And you can see we've got redundancy here. So on PC1, if I was to try to ping PC2 at 172.16.2.2, it still works. And why does it work? It may not be going what was the shortest path because the route between router 1 and router 2 is now down. But it still has a path. It has a new shortest path, right? Because again, the original shortest path is no longer available to us. How can I see that? I could just simply say trace 172.16.2. Oops, sorry. Oh, let me come back here and that's a trace RT. My bad. Trace RT. There we go. So we do the trace, and we can see that I now come over here. I go to 172.16.1.1. That is that gig 00 interface on router 1. That's my default gateway. But now I'm transiting the link between router 1 and 3, the link between router 3 and 2, and then out the gig 00 interface on router 2. I think it's the gig 00 interface on router 2. I'm going out that interface to PC2. And so that's that convergence we're talking about. So back to the conversation here. You'll notice that the timer value, the dead interval timer value did not adjust, right? So now we've got, it's kind of skewed here. And this is a packet tracer phenomena is what we'll call it, undocumented feature that it doesn't do what regular Cisco IOS would do, which is auto-magically adjust that dead interval value to be 4 times the hello interval value. So how do we deal with that? Well, they've got us here on the interface IP Ospf dead interval, and let's set that to 60. So this is not going to bring the adjacency back up between router 1 and router 2. All this is doing is correcting that packet tracer phenomena that doesn't auto-magically change the dead interval to be 4 times the hello interval. So again, remember that in a real-world Cisco IOS scenario, and I probably should start saying iOS XE, but we'll just say iOS, this is auto-magically going to adjust for you when you change the hello interval. Now, why would you want to change? Why is there a command to just change the dead interval? Maybe you don't want to wait 4 times the hello interval. Maybe I'm good with a hello interval of 15 seconds. However, I want the dead interval not to be auto-magically adjusted to 4 times what it is. And so here we are back on real Cisco routers. Do show IP Ospf interface serial 000. You can see that the hello interval, when it was adjusted, auto-magically changed the dead interval to be 4 times the hello interval. But what if I don't want that? I want it to be 2 times the hello interval. So this is going to show us 2 things. The first thing is that I can change the IP Ospf dead interval to be 30 seconds. I can change it to be 2 times the hello interval. Now, the question that you should be asking yourself is, well, wait a second. If you do that, is it auto-magically going to adjust the hello interval to be the divide that by 4? Is it going to change that value, right? So changing the dead interval, does it auto-magically change the hello interval? Well, let's find out. And the answer is no. So we learned 2 things right there. Why does that command exist? IP Ospf dead interval. Why is there a command to allow me to change that value by itself and not have to depend on changing the hello interval, and then the dead interval I just have to accept as being 4 times the hello interval? And this is why. You can change the dead interval by itself without affecting the hello interval. But when you change the hello interval, know that it is changing the dead interval auto-magically to be 4 times whatever the hello interval is. But is that true? What if I was to come back and say IP Ospf hello interval and change it to, oh, I don't know, it's 10 by default. We're going to change it to 5 now. So now the question becomes, I've changed the dead interval and I've hard-coded it to be 30. What if I now go back and change the hello interval? What's going to happen? Does it get changed to 4 times the dead interval? Is it changed to 4 times the hello interval? And the answer is no. So once you manually change the dead interval, when you change the hello interval, it is no longer 4 times. The dead interval is no longer 4 times the hello interval. It is whatever you have set the dead interval to be. So what do we have at the end of the day? Do show run int serial 000, and this is what we have. So now the dead interval is 6 times the hello interval. because for whatever reason, we want to shrink down the hello intervals, the hello packets to go back and forth every 5 seconds, but we're okay if we're missing, in other words, we're going to wait until 6 of those packets have been missed before the adjacency is taken down. So again, semantics, but it's the little things, right? The little things that make the difference, and understanding what is actually happening when we tweak these different values. So let's come back over to Packet Tracer, and we've now got the hello and dead interval set to 15 and 60, right? And we know why we had to do those things. And so now let's step over to adjust the timers on router 2. Now we got to confirm here, router 2's interface is the serial 000 as well. So that is convenient. So we'll come back over here. Let's set the timer values to be the same. Into global config, serial 000, and let's say IP Ospf hello interval 15, IP Ospf dead interval is 60. And again, we're forced to set it to 60 because Packet Tracer doesn't auto-magically do that. Now, there are hello packets that are going back and forth that, as we've seen, are communicating, hey, this is my hello interval, hey, this is my dead interval. And so let's see, and there it is, finally it came back. So let's see what happens, and what happens is we have the adjacency come back up. So do show IP Ospf neighbor. And now that adjacency between router 1 and router 2 is back up. Now, if that's the case, let's see what a trace route, or trace RT for trace route, let's see what it yields now. And Ospf reconverged in here. And Ospf is smart enough to know that the shortest path to get from PC1 to PC2 is not to go this way based off the cost. The shortest path, and yellow-green is not a... Boy, oh boy, I'm just trying to get to green here. The shortest path is to go that way, because this is going to introduce an extra hop if we come over here. And we don't need to go that way. So we've got redundancy. We also have Ospf guiding us to the shortest path, and now that is back up. So the final setting that we're going to talk about, and again, this is one that I wish they would provide a little additional context around, and that's we're going to adjust the bandwidth setting on router 1. So trace the path between PC1 and the web server, right? So easy enough. We'll pull this back up, and we'll say 64.100.1.2. So where do we go? Well, we go from PC1 through switch 1, sorry, keep this centered here, to router 1, to router 2, out to the web server, right? And you can see right there, there's the default gateway address for PC1. Here is the interface over there on router 2. That takes us out to the ubiquitous internet cloud, and then out to the web server. Now, when Ospf is making decisions as to what the cost for certain routes are, let's take a look at the routing table here first before we get into this manipulation of the bandwidth setting. Because if we're doing this on the serial 000 interface, which is going to be this interface right here, right? Remember, when Ospf is calculating the best path, it's based on cost, and that cost is derived or arrived at by looking at the bandwidth of the interface, and then we're taking a look at dividing by 10 to the 8th in bits per second, right? 10 to the 8, and the unit we're dealing with is bits per second. And so let me flip back over here, because let's go ahead and say, do show IP route. What does the routing table on this router show right now for the default route that's being received? If we were to come up here to router 2, rest assured that there is a default information originate statement in here under the Ospf configuration. And there it is, default information originate. And it's originating a default route that it has configured on router 2. And again, this default route here just says, hey, my route, if I don't have anywhere else, if I don't know where to go, and I don't have a longer, more specific match on how to get to where the packet's trying to go that I'm routing, shove it out the serial 010 interface. And that happens to be this interface right here. Send it to the internet. And you can see right up here, serial, router 2. Yeah, serial 010, it's right here, and that sends us out to the 209.165.200 network to the internet, right? And so router 1 is learning that route, and here's the administrative distance, right? And here's my cost, and here is the interface out which OSPF wants me to go to get there. So let's pay very careful attention to what happens when we manipulate the bandwidth. Now, let's take a look at router 2's routing table as well before we step off. Do show IP route. And let's see what router 2 thinks is the quickest way and the shortest path to get to the 172.16.1 network, this network over here behind router 1 that PC1 sits in. And it says, well, I'm going to go out the serial 000 interface. I'm learning about it, right? From 172.16.3.1, which is this IP address right here on router 1. And so that's where router 2 is going to come back because it has a cost of 65, right? To come across this serial link. Meaning the cost of coming down here to router 3 and over to router 1 is not better. So let's see what happens now. So on router 1, we're going to pull router 1 back up here, and let's get an interface. I think we're already in there, but let's confirm we're in interface serial 000, and that's where they want us to be. I'm just reading through this real quick. All right, so we've already traced the path. We know we go up to PC2 because it has a lower cost. So now we're here on interface serial 000, and again, to see the bandwidth, just say do show interface serial 000. What is the bandwidth setting that I have right now? Well, we just pop this up and we can take a look in here and see that the bandwidth is right here. And this is our sort of default T1 of 1.544 megabits a second, but the value is displayed in kilobits per second. And we're about to change that. So we're going to say bandwidth, and what is the unit of measure that we enter the bandwidth value in? Well, it's kilobits. So I'm going to say 64 kilobits a second. And this is a huge step down, relatively speaking, from 1,544 kilobits a second down to 64. And what is that going to do? Well, what that's going to do is it's going to make OSPF reconsider what the shortest path should be. Now, if it's 64 kilobits a second outbound on this interface and it's 1.544 megabits a second, or we'll leave it in kilobits a second here, 1,544 kilobits a second to go this way, then we could probably easily draw the conclusion that the lower path with a higher amount of bandwidth available based on what the default is, because we didn't change this interface here, right, that would be the preferred path at this time. So let's take a look now on PC1. Let's rerun that trace to the internet, and where do we go? We go out the interface that leads us over to router 3. And then we go to router 2, and then we go to the internet cloud, and then out here to that internet web server. However, this brings us to a very important conversation. I've changed the bandwidth on this side, but I never changed it on this side, on router 2. So this would be interesting to come to router 2 and to say, do show IP route, and let's see what router 2 thinks is the shortest path. Well, it still thinks that the shortest path is to go over here to get to the 172.16.1, which is this network behind router 1. It thinks that the shortest path is still to go through the serial 000 interface. So I'm going to do something here because I want to see if in fact that is what is happening, or if packet tracers kind of hung up here. So let's go ahead and say do clear IP OSPF proc, and I'm going to say yes. It's going to take all the adjacencies down, but it's also going to then bring all the adjacencies back up. So I'm basically on router 2 just clearing all of the adjacencies, right? So router 2 sees that the outgoing cost here is going to be 64. And what I want to prove to you is that it's not that we've got some sort of a hang up here, and hopefully this is going to come back up here in short order. We're still waiting on the adjacency between, I believe, do show IP OSPF neighbor. And we are still waiting on the adjacency between router 1 and router 2. And the reason I wanted to show you this as to why router 2 still thinks that the shortest path is coming back to router 1 via this link right here is that OSPF bases its cost calculation on the outbound interfaces. So router 2, the bandwidth here is still 1544. It never changed. So router 2 believes that this is in fact the shortest path, even though it has, on this interface right here, only 64 kilobits a second. And now it looks like we're going to be, are we stuck here? Yeah, and the bandwidth doesn't have to be the same, and the hello and the dead interval, we might be waiting, and we'll give it a couple more seconds, but we'll talk through this, and this could be, again, this is a packet tracer phenomenon that we're dealing with the adjacency just taking too long to come back up. So when we set it to 64 here, if this is in fact 64 kilobits a second, if this is in fact all that this link is capable of, do not only set it on one side. For the reason I just pointed out is that all traffic coming in from the internet and all traffic from PC2 that's trying to get to anything over here on this network is going to come this way. And if it's only 64 kilobits a second, we don't want that. We would prefer that it come this way. Even though it's an additional hop, right, you would want to set this side to 64 kilobits a second as well. Now, the most important part of this conversation, in addition to making sure that if it's a 64K link or whatever it is, 512, 256, 768, whatever it turns out to be, that is when you would change the bandwidth setting, is to accurately reflect whatever the true bandwidth of the link is. And it is in that case and only that use case that you would want to change the bandwidth setting. Because changing the bandwidth setting has other impacts that you may or may not be aware of. And one of those is quality of service. If you have QoS configured, and you're trying to do layer 3 traffic engineering with OSPF using bandwidth, you could be hosing your QoS configuration. You wouldn't want to do that. The way that you would do it is by using the IP OSPF cost command, because that only impacts OSPF. So QoS is one thing that you can completely hose. The other thing that you can completely hose would be, what if we're running another routing protocol? Maybe EIGRP is configured in our environment and we're doing OSPF. And so we're running these as ships in the night, right? You know, OSPF is running and EIGRP is running. And I use the ships in the night analogy for a reason. And that is because if you start tweaking the bandwidth setting on router interfaces, trying to manipulate layer 3 traffic engineering for OSPF, you might unknowingly be tweaking and impacting the layer 3 topology for EIGRP. And that could result in your OSPF ship and your EIGRP ship, which would be ships in the night, colliding together and sinking each other, right? It's a race to the bottom of the ocean if you're going around and tweaking the bandwidth as a layer 3 traffic engineering approach. Now, is there some corner case out there where maybe this is the only way to do it and this is how you want to do it? quite possibly there could be. However, on the whole, you're going to be using the IP OSPF cost to make your layer 3 OSPF traffic engineering decisions and changes, and you're going to be using delay to do EIGRP, because OSPF doesn't care what the delay on the interface is, and EIGRP doesn't care what you set the IP OSPF cost to on an interface. So again, I really would have liked some additional context around why we're making this change and when you would want to make it, right? You only want to adjust the bandwidth on the interface when, in fact, that is the bandwidth that interface is capable of. And this is a great example of why you would want to do it on both sides, so that both router 1 and router 2 and OSPF understand that this link between router 1 and router 2 is not the best path, and that we would prefer to go around to router 3. And in fact, let's see if OSPF can make that happen. So interface serial 00, bandwidth 64. Now let's give it a second here. And again, the path between router 1 and 2, it doesn't look like it ever came back up, and it didn't. And that's, we're going to, or actually, no, I'm sorry, it did. 172. I did not say, I was looking at this thinking that this was out to the internet. I apologize. So the adjacency is back up, right? But let's take a look at that routing table now and see what is the shortest path to get to that network. Remember, it's the outgoing interfaces that router 2 is looking at here, looking at the bandwidth to calculate the OSPF cost value out each of these interfaces, right? And now it says, whoa, wait a minute. Now this is set to 64, but that's what we want. We want it to take the quicker path, right? And again, maybe if this was a leased line here between 2 and 3 and you don't want it to take this path, then you wouldn't set that to 64 here on router 2. Again, I'm going over the most common use cases that you'll be dealing with as I'm trying to adjust the picture here. And again, as you can see, that is the path that traffic is now going to take when it's coming back through router 2. And so, again, you would want to set it to be the same on both sides. All right, well, I think we've covered as much as we're going to get out of this activity. Let me clear my screen here and get control of the mouse. So that is basically everything we wanted to cover there. Again, some very important semantics, the little things that make the difference in making the changes. All right, well, that is it for Packet Tracer Activity 7.2.1, Configuring OSPF Advanced Features. Thank you guys so much for watching. Best of luck throughout this semester. And that is all I have. I hope to see you in the next video.